So this is the last two talks for today. One will be remote and the other instead in person. So the speaker is Jeff Byers from NRL in Washington, right?
That's right.
And also Jeff likes to spend quite some time, several years, I think, at the University of Padova. And he will give this talk remotely, but he will join us for the workshop starting from next week or the one after.
No, next week I fly in this Friday.
Okay, so for those who will be here, it will be an opportunity to discuss more with him. And your talk is 30 minutes plus 5-minute questions. So if I see that you start getting late, maybe I will remind you 5 minutes before the end of the 30 minutes. And the title is Using Machine Learning for Physics, the Underlying Mathematical Assumptions. Please.
Okay, so good afternoon. Just very briefly, my background is probably a little bit different than the rest of the participants. I got my degree in theoretical physics maybe 28 years ago, okay? But for the last 14 or 15 years, I've been dealing with machine learning. And I've been dealing with it in many, many different contexts, not just scientific applications of machine learning. And I've seen whatever it is people like to call machine learning evolve over those years. And so now it's something a little different than it was when I first was dealing with machine learning. And I'll try to outline that just a little bit. But I want to start with something that's important, I think, for physicists to realize. This is a quote from the famous philosopher and linguist Ludwig Wittgenstein, where he said, "Philosophy is a battle against the bewitchment of our intelligence by means of language." But I would transform that into something that I think physics learned in the 20th century, and it's very important for applications of machine learning in physics. And I think Albert Einstein would probably agree with this, because he really was the one who figured this out, is that differential geometry. Geometry is a battle against the bewitchment of our intelligence by means of coordinates. Now, all these machine learning algorithms that people are talking about, they come from mostly the computer science community. And this community doesn't really think about this distinction. And so as physicists, I think we're uniquely positioned to realize that this is vital. Coordinates are something we make up. They aren't something in the world. They are a kind of way of organizing what we're doing, but we should be always very vigilant not to be tricked by the nature of our coordinates. And that's one of the problems of machine learning. It can be easily tricked by the coordinate systems you're in, and not having equivariant coordinates and dealing with that properly can lead to all sorts of odd and strange problems. So very briefly, I know perhaps everyone knows a lot about machine learning, but I think it's worth briefly taking a tour of machine learning to make sure we know what we're talking about. In general, machine learning that gets used probably in physics has these forms here I'm describing, where there's supervised and unsupervised learning. But maybe something that physicists don't think about is that there's discriminative and generative forms of machine learning too. So consider this field of dots over here, where I've colored them as if they were labeled. And we imagine we look at one of the more common forms of machine learning, which is discriminative machine learning. And this is generally just saying, I want to find good boundaries between the colored dots in whatever space they're sitting in, okay? Now, if I remove the labeling, that tends to be what's called unsupervised learning. And that's where you're saying, well, I want to find some way to represent the data by structuring it, but I may not have a model to create the data. Now, if I move into a generative type of model, as the name implies, this is a model that's able to generate the data. Now, this is what physicists mostly think about. Physics models are generative models. A physicist isn't going to be happy in general with a discriminative model. And finally, if we look at the geometry of the generative models, we see they're generally more centered around archetypes in the data sets. It's almost more like clustering or density estimation. And so the geometry of discriminative learning is generally about boundaries, where generative models tend to have sometimes probabilistic structures, and they tend to be more centered around certain sorts of archetypical data with some spread around it. So it's good to understand that these are some of the major distinctions in machine learning models. There are many other forms of machine learning, like reinforcement learning and other things, but I don't think we need to go into those right now. So if we take these two major forms of machine learning, supervised learning and unsupervised learning, and under supervised learning is a lot of what people do, where it's just regression. So for me, a definition of machine learning that seems to work over time is it's high dimensional nonlinear regression that usually ignores uncertainty estimation by doing some sort of optimization procedure to help speed things up. So in general, machine learning tends to not be as interested in uncertainty quantification and more interested in point estimation in a large high dimensional parameter space. Now, recently, this sort of has changed around where we're talking about, this merger of like there's artificial intelligence and then there's machine learning. And then of course there's deep learning, which has been around for pushing almost a decade now. And then there's neural networks. And so there's been a tendency in recent years that people think machine learning is neural networks, which for me is kind of confusing because I never thought of it that way. It's just one of many representational systems you can use in machine learning, but it's become more dominant. Now, just as people may not know this, it's like neural networks died twice before. They were sort of destroyed by other techniques. And originally when they came up in the 50s and 60s, they failed for certain reasons that I don't have time to go into now, but if people are interested, we could talk about it when I'm on site. But this is the third go around for neural networks, and one of the more robust, because finally the computational power is caught up with the complexity of doing back propagation across these things. So just briefly to describe, a neural network, which is what a lot of people are using, it is a rather strange object from the standpoint of a physicist, because that question I raised about coordinates and being careful about not being controlled by your coordinates, it's this notorious sigma dot object that gets used when they're building the underlying structure of a neural network, which says, I will apply a nonlinear transformation to an affine transformation that I've written here, Wx plus b, and you apply it though, this I is the free index here, to each coordinate. Now, this is a really rather strange thing. I would say there's nothing in the physicists pretty much never do this. To say, I have a nonlinear transformation, but I'm going to pick off each coordinate and apply it and output that. Okay, so, you as physicists, I would claim you should be very uncomfortable at this point. How will you maintain invariances? How will you maintain various structures that we expect inside theoretical physics models? It's not at all clear how a neural network can do that, okay? Or it has to have a very complex representation to do it. Another thing that happens is you use a cost function. Now, typically this cost function that people often don't even talk about what it is. It's just sort of like this mean squared error of the outputs versus what the network does. F of x is the network that I'm showing over here, this neural network. And these outputs are things you'd like to match. Well, you apply this cost function. Does this cost function have anything to do with what you care about? Do you believe that this cost or risk function, as a statistician would call it, is shaped like a parabola? Maybe not. The other funny thing is that learning in a neural network, you often think of it as an optimization problem. Well, at least in deep learning networks, it is not really an optimization problem. It is something much, much more complicated. It's like a high dimensional dynamics that finds a limit cycle around a multitude of different possible solutions that you claim are similar. So it's a very complicated solution that these systems find. And then you believe in gradient descent, which means you have to have differentiable structure. So do you have differentiable structure? Well, you better have it, because that's what these kinds of systems depend on. So one of the problems with the geometry of a neural network, to pick on them just a little bit more, and I'll switch to a more general setting and talk about geometry in a moment, it's that mostly data lies on low dimensional manifolds. And this is because in the generative model, the number of parameters to generate is nowhere near the number of things a sensor or an experiment could see. So your data sits in the space of the data space the sensor could possibly see, and it's very small, a incredibly small measure in this astronomically large space it sits in. And what happens is that neural networks like to use these functions over here mostly, like sigmoids, tangents, and the most popular, the ReLO, the rectified linear unit, this one, the third one here. And they're actually non-local representations. They're more like I was showing those discriminative boundaries. They're sort of looking for a hyperplane that's lined up to some boundary. And then you have two regions on either side of it. They don't generally use these radial basis functions because they take longer to evaluate, but they're a little bit different from what I'm saying here. But what happens is when you use neural networks, you sort of end up like slicing up your space with these planes. Well, on one side of it, you may have no response. On the other side, you have a response. But the problem is it generates these very high dimensional corners in your space in the geometry. And as you may know, in low dimensions, it's not a big deal to have corners. You know, if I put a sphere in a box, the sphere takes up most of the box in very low dimensions. But as I scale the space to thousands or millions of dimensions, all the space is in the corners of the box. And the problem is that you may never have seen, you know, like in the case of a high dimensional multi-layered neural network, like I'm showing here, that's like, this is just an example where you think of it for like facial recognition. When you do this, you end up with this weird problem of finding the network believes in things that are really crazy. Like this is a neural network that believes that what I'm showing you here on the right are the digits 0 through 9. It has high confidence that it believes these are the digits 0 through 9 on the right. And on the left here are various images that it thinks, well, these are these objects here. And we look at them and go, well, the top ones look like noise. The bottom ones are like, well, maybe I can believe there's some sort of texture that looks like the object. The stuff on the right here is like very hard to discern. And the reason that this happens in neural networks and deep learning is that there's a problem with how you regularize and you measure the bound, you get your boundary right. And when you train with your data in a neural network, it doesn't necessarily guarantee that your boundaries of distinction, where you line up all these ReLO functions or tangent, hyperbolic tangents, or whatever you're using, that they really cut through the data in the way that's the most robust. And so people have known for many years now, it's easy to trick neural networks, like adding a piece of high dimensional noise perpendicular to one of these boundaries, like on the right here. I can take a pig and turn it into an airliner by just nudging the data just a little bit out of this hyperplane and across a classification boundary. And so this has raised enormous concerns for people using neural networks. I don't know how much the physics community realizes that this goes on. It may not affect low dimensional applications of neural networks that much. But the problem is that we have a computer vision system in our brain that can realize that pig is not an airliner. I don't know what it looks like when you're looking at abstract physics data from like the Large Hadron Collider that, you know, something like this happens, because I'm not sure anyone has that kind of intuition, right? It's so much more abstract a problem. But you have to realize the geometry of neural networks have some very peculiar properties, and it's due to this non-local structure. So I'm going to shift now to talking a little bit about, well, okay, fine, that's what machine learning is a little bit like now. What is physics, if we think about it a little more abstractly? And so I would say physics is sort of this model here of like a bottleneck, where we say we have experimental data, and this is drawn, if people know about this, as like an autoencoder architecture. So I sort of mimicking an autoencoder system. And so you have a bottleneck of some kind, and that's sort of the parameters of the model that can generate the data. So you can say, I use my data to find the parameters X of the model, but I can decode them, which basically means I can create simulated data. So I use real data to find the parameters of the model, and if I want, I can simulate data on the other side in the decoder. And so this inference step and this model step is sort of what's a little bit, it's very interesting. It's like the fitting versus the simulation part of the problem. Now this is not just a vague diagram. You can actually try to figure out how do you mathematically do this. But one of the most important things is that this word at the top here, relevance, this relevance here. And this relevance term is sort of latently understood in physics, but it's often not very explicitly understood. So if I wanted to mathematically represent physics as a system, where I thought it from a information theoretic standpoint, which means the conservation of mutual information between different representations, you sort of think of it like, well, I have some data, let's say this Y variable here. I want to make some representation of it, but I want to make this representation such that I preserve some sort of relevance. There's something I care about the data that I'm trying to preserve. Now, in the world of machine learning, like for classification, these are labels, so I just put labels here. But these don't necessarily have to be discrete. They can be more like a function too, like you're doing regression. And so this relevance here is something you try to preserve as much as possible while you have an efficient, compact representation of what's going on. And there's systematic ways to do this. And machine learning is one mechanism to be able to try to preserve this type of relevance systematically. Now, relevance, I've uploaded these slides. You can look at these slides at your leisure. And when I'm actually there, I'll give a longer talk, I think, next Wednesday after this conference. And we can come back and talk about these things. But I just wanted to point out of what relevance is in data. It's very important, this last one, relevance as distinguishability, okay, in the data space. And this means that distance metrics are very important. You have to understand how to compare 2 points in data. And this is important for machine learning and all kinds of statistical analysis. And so this is a key point of understanding my first statement about geometry and coordination. You need to understand what it means to put your data into the space and then do the machine learning on it. So in a very simple case, mostly this relevance is the preservation of some property that we care about. Like, let's imagine we have something like quantum electrodynamics, that representation of electromagnetism. And so on the left there, yes, we have quantum field theory, right? That's the more fundamental way to think about things. But we certainly spent a lot of time learning classical electromagnetism and Maxwell's equations, right? Not even necessarily in an F-mu covariant formulation. But that doesn't mean I want my quantum field theorists to design the antenna for my cell phone, right? And so I actually have to figure out, how do I compress these models down for a particular use, like in the case of an antenna. So the equations are very different. The models look very different. Even though we know in a reductionist sense, we can go from the equation on the far right back to the equations on the far left, as long as we're good at unpacking all the symbology. But there can be very important differences at every level as you do the model compression. Many aspects of physics are related to that idea of model compression. So this is, to me, these diagrams help me, and I use it when I'm talking to students and others to say, well, what is physics and machine learning? Well, it's really, the physics is mostly thinking about the generation of a model. Physicists have good models that they come to the table with. This is not true in computer science. And so machine learning is formulated where you kind of reverse all the arrows and just say, there's not a model, but there's a bunch of features. There's these latent features hidden perhaps in the middle of your neural network. But we're again trying to always use this relevance, this part along the bottom here between data and something we care about, to be able to say, well, are we preserving the thing that we're trying to, that we care about? And so even though physics looks more at forward models, and machine learning is more inferential-like in its behavior, I think it's important to understand this sort of distinction about whether you bring models to the table and have them to use, or whether you're just purely non-parametrically finding features. That's an important part of what machine learning is doing different than physics. So the geometry of this is interesting, because in the world of machine learning, there's a complete belief and faith in linear algebra and multivariable calculus, right? So everything is usually differentiable, and you can use linear algebra wherever you want. And so you're basically in this giant vector space, RD here. And the question is, well, are you? Like I have this example here, like, graph neural networks, which have become popular recently, and other types of graphical objects, and you're trying to shove them into vector spaces, basically. Every crazy thing you could think of wanting to do a model of or inference on, when it comes to machine learning, it gets stuffed into a vector space. Now, is this stuff a vector space or not? Well, strictly speaking, no, right? It's probably not a vector space, but this is the central mathematical conceit of machine learning, is that I can take my data set, and even though it's a tuple, like an n tuple, like I just have a row of some numbers, and I claim that that thing is a vector, and I can apply the properties of a vector space to combining the data, adding, subtracting. It has a zero, it has an inverse, all scalar multiplication, all the things that a vector space is supposed to have mathematically. Now, this is not true, but it could still be a useful trick, right, that machine learning is doing. So here you're trying to say, yes, look, I map it to this RD space, and I still have this relevance I want to retain about my models and why am I even doing what I'm doing, right? This relevance component of the diagram. And over here, I have to sort of say, well, we're not going to jump across here so easily, right? So we have to figure out how we're going to learn a representation, which in general is probably a constraint manifold on the parameter space that the data is sitting in. And so you have to learn kind of like an injective map, which is the manifold being shoved into this huge RD space. But you may also want to learn maps that do the compression of my model, which is saying, well, I don't care about everything about this manifold. Maybe I only care about some of it related to this relevance. So the key thing here is the similarity. When we're comparing the similarities, and if you know anything about information theory, it's really best not to compare probabilities, but minus the log of a probability. That's actually a better measure of the information content of a probability. And so you're saying that minus the log of the probability of two pieces of data being similar is related to some kind of distance function, squared. And so you say, well, we'll approximate that as this difference between the two, as this kind of Euclidean L2 norm. And we'll say, yeah, minus log P is kind of like this difference over here, on the right. And that's kind of at the heart of machine learning, that statement right there. So if I go and I take that statement, I say, well, it's about data's closeness or farness. If it's far away in whatever the space is, I say it's statistically dissimilar. If it's close, it's statistically similar. So you can see that it matters a lot. What is your data and what is the space you put it in? Because if you don't understand that space, you're going to mess up this Euclidean ansatz about your data, because this is central to being able to do this. So what happens is that, and this is this problem that every time I've done a machine learning project, this is one of the first questions that always comes up is how much data is enough, right? How much data do I need to do machine learning? And of course, the answer is, I don't know. Because it's related to something that we don't know about your data, which is the interplay of local noise with curvature within that manifold. So I'm like, well, in order to do what you want with machine learning and physics, you need to make sure that the data, there's enough data where there's curvature so that we can see it to find the manifold that you care about. Now, if there's places that are relevant to what you're doing, you don't have to do that. But for those places that it matters, you have to find and detect this curvature statistically in the point cloud. So this is a challenging problem to know as you move between this noisy structure to this manifold structure in low dimensions in the space, how you reliably detect that locally. So let me talk about something else that often gets put by the wayside, is that you go and do machine learning and it's not clear, what do I do with my hard to obtain, difficult experimental calibration data? Machine learning is not well suited to dealing with calibrated data. You typically forget about the calibration and go to step 2 and say, well, it's just a measurement. We have some data, we're going to fit some function to it. And that can work or it may not work. And the key is to understand when and why that's true. So here's just my kind of schematic with saying, well, when we do calibration, we're really putting in a known calibration source like X calibration, and we're saying we know why, that's it because you're measuring it, And there's some parameters of the instrumentation that you want to figure out, alpha. Now, these are granted, they are nuisance parameters that you would like to marginalize out. You'd like to create something like a marginal likelihood over it and get rid of them, but they're still, you have to know them. They're a source of, uncertainty in what you're doing. And then when you do the measurement, you say, well, I could fix alpha, or I can marginalize over this alpha that I learned in calibration. And now I go and do my real work, which is saying I measured Y. Can I infer something about X that is the hidden variable or the parameter, the thing I haven't seen? So, the question is, did my calibration cover the data? Am I able to use it? And this is part of the challenge with machine learning. And so just imagine I have these various calibrations here, so they're actually like covariances. And so this is a 1-1 tensor field of covariance over a simple two-dimensional parameter space. And then I could say, all right, well, these are very different calibrations. How will I use this in what I'm doing? Or why does it matter? Well, it matters because this calibration is related to the metric tensor in the space and for dissimilarity. If I'm trying to compare data and I throw some data here on top of these different covariance fields, they're not in the same space anymore. Each one of these is actually, if I transformed back to a Euclidean flat space as best I could in a local chart, I would see that the data don't look the same. Here it's the same data, but I'm showing you the variation of the covariance field behind it. Now there's a way to go in and learn the Jacobian of the transformations to make sure the Euclidean form that machine learning wants to use is true, but not doing it is ignoring vital information. Now, it may not matter, okay? It may not matter if you have enough data and you're looking locally enough, then every bit of the space looks like a tangent space. And you can say, yes, if I only look locally and I have plenty of data statistically, I don't have to deal with this because I can just say that it's flat space over the width of my kernel or wherever I'm looking, okay? And that's fine, but what if you need data efficiency, or you don't know if you have enough data in every place? So this is like, it's something you should consider. Don't ignore your calibration data. So, I probably won't get through all this, but we can talk about it in a longer talk. But there's also the idea of saying I can use one of the concepts that's very powerful in physics, which is fiber bundles with the manifold, and understand that the thing I care about may be a base manifold to a restructuring of my original data space into a fiber bundle. And this essentially means that where this MR is the compressed model space, the space where I'm like, if you will, of my labels, so I can change labels by moving within this MR manifold down here. But if I move along these fibers, they're actually symmetries. They're symmetry operations that I can do to my data that don't change the label, okay? And so the relevance is only down in this plane, in this base manifold of the fiber bundle, but all these other things, they don't matter. You can almost think of this as very similar like a principal fiber bundle where every one of these blue fibers is like a Lie group that I can act on my data at, but I say that it's a symmetry, that it doesn't change my relevance. And so this is a powerful way to understand when in my similarity measures and when I'm doing the geometry in my machine learning, how should I think about what I'm learning and what is the goal? It's to be invariant to certain things. Now, I have an example here. I'm not going to go through in detail because of time constraints, but it sort of says, well, if I did this for a simple classification problem, like with types of triangles, equilateral, isosceles, right scaling, and I imagine a massive data set of triangles just for fun. And I said, well, what manifold are they on? They're obviously on the manifold, constrained by their interior angles being summing to pi. And they're subject to these transformations. I can translate triangles, I can scale them, I can rotate them. That doesn't change whether they're scaling or isosceles or right triangles. And so what you have is you have the Lie group fiber sim, what's called sim2. That's what these blue things are. They sort of sit connected to the space. Just kind of like how in physics, fundamental physics, you have space-time and you attach the standard model fiber, right? SU3 cross SU2U1, and you have those fibers attached everywhere in your space-time. And so here, computer vision is actually Sim3. When you do computer vision in machine learning for object detection, you're trying to be invariant to the group Sim3. I should say, yeah, the sim terminology is probably not familiar to physicists, but it's just saying you have scale invariance and rotation invariance and translation invariance and however many dimensions you're working. And so this is a way to think about how, in a funny way, computer vision is a lot like the standard model when you think of it as fiber bundles. And you're trying to learn this separation of what is the base space where I would do like object detection versus what are these fibers that I need to be invariant to. So in closing, this is the last slide. Physics and machine learning, it's an interesting connection, but I'm very cautious about just applying machine learning to physics. Because machine learning is this sort of, it's when computer scientists didn't want to really learn, or they didn't like the way statistics was being done, mostly I would say in the 80s and early 90s. And they sort of reinvented statistics, but more in a high dimensional setting and more what statisticians would call exploratory data analysis. Not decision-making analysis. And that's an important point. It's like there's a much looser criteria in machine learning than in classical statistics. Now, in the natural sciences like physics, yes, we mostly use parametric models, which means a finite number of parameters specified before we even start doing anything. And there's also a sense that we're not really trying to look at just correlation or association, but we actually would like to learn causation. I don't know if a lot of the enormous amount of work that's been going on machine learning or learning causality has been transferred into physics yet, but it's a fascinating field to understand how to use probabilistic graphical models to infer causality in systems that physics should start to become aware of. But physics, going into the world of the non-parametric while retaining explanatory power. You do not want to give your life over to black boxes in machine learning and lose your explanatory or interpretability aspects. But you may want to say, well, I want to be more non-parametric. And all non-parametric means is lots of parameters. And the number of parameters is defined by the complexity of the data. That is not something physicists are used to, by and large. They're used to fixed parameter sets for fitting. It's more, physicists think we're more like they're fitting curves. Non-parametric fitting is a rather different business and requires some rethinking, but it's very powerful. And it's a big part of what machine learning does. But machine learning, it really puts its emphasis on prediction. It says, you may not know why this is the prediction, but we're just going to try to be as accurate as we can with a more complicated model. So I would say my interests are, I would very much enjoy talking to people about it, to all of you about it, is that we need an alteration in how you do machine learning to make it fit the needs of physics better and to operate in this boundary up here of the non-parametric, yet trying to understand how we retain the relevance and explainability of our models. So that's it. I think I'm roughly on time. I know that was a lot kind of quickly, and I'll be happy to talk about it, but this was more of an overview. I would just, as a brief advertisement, I would say on a talk that I'll give, I think it's scheduled for next Wednesday, September 14th, as I'll go into some of the interesting geometries like information geometry and how you can think of these spaces as, having curvature and manifolds of probability distributions, how you interpolate calibration and uncertainty covariances in these spaces and try to understand them as in distances that are measured in bits between different representations. And so there's a lot of mathematical aspects to this that I think are very valuable for physics to know. They've sort of been lost in, how they were developed initially, machine learning prior to deep learning, but I think physicists will benefit from it and really understanding how to create more local models and representing the data, because I think this is very important for finding new physics for things like anomaly detection. So I'll stop talking at that point and just sort of go back to this slide. And if there are any questions, I'd be happy to take them. Thank you.
Thank you for this, I hope, inspiring talk. Questions? There is one on the bottom now. Aspect. Can you pass the microphone?
Thank you for the great talk. I was interested in this last bit you talk about of dealing with causation. I saw it more in other areas, not so much in physics. What exactly are you thinking? Where could we apply causality studies that places?
I think that you would like in physics to have a sense of causality, because causality, it sounds very abstract. When physicists think of causality, it is a little vague, but in other areas like in medicine and sociology and psychology and other fields where you don't have the fantastic experiments that physicists are able to do and the amazing models, they're sort of rooting around in much trashier data. And they actually have to become much smarter about saying, well, how do you define causality and systematically detect it? And so physics is kind of funny, where maybe we gave up on causality because of quantum mechanics and, quantum field theory thinking, which I would argue is a little bit, I think, of a mess where physicists think of probability in very strange ways. It's like I felt like I had to unlearn how the distortion of quantum mechanics made me think about probability, and destroy the sense. It's like inference somehow magically became causal, in quantum mechanics. And so it's this sense of finding causation, because what it is, in a machine learning sense, is you're learning modularity inside probabilistic graphical models. So you're trying to say, if you think in a Bayesian way, it's saying, where could I change the prior, but the likelihood stays the same? And so it's learning the stability of the likelihood portion in a probabilistic graphical model and saying, well, this can be put into other situations. And that kind of is what causality functions as. It says it's not dependent upon the prior, but it's just the likelihood as a modular object that's stable across many applications. And so I would say that's captures in a rather abstract way of stating it what's most interesting about a physics model. A physics model is able to be applied to many different initial conditions. That's kind of like the prior. And so I see returning to thinking about causation and using machine learning to detect this in data to find this modular stability is a very interesting and powerful approach. Does that kind of clarify what I was suggesting?
Yes, thank you.
So if you have still time.
No, please.
Here Alessandro Candido from University of Milan. So I have a kind of more mundane question, in the sense that the talk is extremely inspiring, and having a deeper understanding of what is going beyond, it's for sure amazing and can help in also find a better way to deal with different situations. Problem is that one good thing of machine learning is apart from giving very powerful techniques and so on, is also that gives practitioners some recipes they can apply in order to obtain kind of results. So maybe they're not always the best ones, and lacking understanding for sure is also harmful. So from your deeper insight, do you have any suggestion, advice, whatever, that translate in practical recipes people can apply in order to improve their inference?
So it's interesting that it's like a big ecosystem, the machine learning now, mostly based on Python, and so you have to ask yourself as a physicist, when I use a black box, how comfortable am I? Like, for instance, I don't think any of us would be that uncomfortable. We said, I'm using numerical linear algebra. I'm using something based on LAPAC or BLOS, you know, these tools that have been around a long time in numerical linear algebra. You build airliners with them, you built your cell phone with them, and coding architectures and bridges, and you know, we're like, we bet our lives on numerical linear algebra, right? Would you bet your life on machine learning? You know, would you use it in a critical application? And, you know, would you say this helps me to understand something? Now, I understand the efficacy of fitting, and I understand that it can be, you know, it can help to use machine learning. But my experience over years with machine learning is when it works, you're happy. And when it doesn't work, you're not happy. And you don't know really why in either case it did. It either worked or it didn't work. And it's hard to fix. If whatever you're doing didn't quite work, for some reason, the inductive bias of your neural network is not lined up with your data in some way that it's hard to specify, it doesn't work, and it's very difficult to make it work. So what I find is a kind of funny thing that people do, which is they take all the machine learning algorithms they know, which can now be all called at once on your data, and they make giant plots of every output, and then they find the ones they like and pick them out and say, yeah, that algorithm was the best algorithm for my problem. What they're really saying is whatever the underlying geometry of that machine learning algorithm was, perhaps had a better inductive bias to whatever it is that I expected to see. And I'm not saying people shouldn't try that and do it. I see mostly people do it all the time, but it is something to have some caution about, you know, to sort of pick out what looks right. It's, you know, remember Feynman said, it's like, you know, it's easy to get fooled and you're the easiest one to fool, you know, yourself. And machine learning, you have to use it very carefully. And I'm just talking from the standpoint of, yes, try it, but be cautious. I have seen it fail spectacularly in places, and I've seen it do amazing things, but it makes me very nervous when you can't tell which one you're in, which situation. So I'm just bringing a note of caution about machine learning and saying maybe there's some ways to make it, to protect ourselves, at least in physics, from it, you know, and be able to be more careful while experimenting and doing exploratory data analysis. I wouldn't stop you from doing it, but just a note of caution is what I'm bringing. Over.
Okay, thank you, Jeff. There is in fact other questions, but since you are coming here next week, we will, I think, have a lot of interesting and funny conversation. Thank you again.
All right, thank you very much.